Good afternoon, everyone. My name is Arturo Ortiz Tapia, and this talk is titled Modeling Human AI Survival with Feedback and Entropy Tools. I'll share a condensed 20-minute overview of how we can formalize human AI coexistence using measurable signals rated on verifiable intent. The work is computational, conceptual, and regulatory in spirit. This is in a way inspired by a talk by the Professor Richard Chamberlain from the United Kingdom, who made a similar talk, and he used different mathematical tools. So I made my own version of it. So motivation and oversight limits. We often hear that AI alignment is about intentions, but intentions can't be fully verified. Gödel and Turing already warned us some truths can be proven and some programs never halt. So instead of aiming for total verification, we measure entropy and energy, observable proxies for drift. The goal is robust coexistence through interpretable feedback loops. And what we have in here is just some of the symbolics that either Gödel or Alan Turing were using back then. Now, the regulated three-species dynamics. Here, here's the backbone of the model, a Lotka-Volterra type system with three agents, humans, that is the XT, AI, YT, and a regulator, Z of T. Saturation terms prevent runaway growth. The regulator moderates both humans and AI and reacts to AI intensity. Think of ZT as an adaptive oversight function, not a sensor, but a dynamic moderator. So here we have the deterministic population time series. If we see at the graphic, but we see the behavior of humans, AI, and regulator. The So let me see if I can shrink it a little bit smaller. Okay. Right. So basically, is this that they stay regulated to each other. So monitorable aggregate signal. If we add all three populations, we get W of T. If derivative is an early warning condition, I don't have the presented that as a slide, but the point is that when the human regulatory terms start approaching the system growth cap, that's where intervention should begin. They give us as handle simple measurable thresholds instead of opaque ethics. Now, the next slide is about the 3D spiral phase portrait. Okay, we have it in here, the 3D spiral. And if we, in the deterministic regime, all trajectories remain bounded. The regulator's feedback keeps the human and AI populations coexisting without collapse or dominance, an important sanity check before adding stochastic effects. Now, about the spiral itself, if we visualize the system in 3D, human AI regulator, the trajectory is a spiral inward. That's a signature of a dissipative system. Energy is lost, but stability is gained. In plain terms, feedback prevents extremes and guides the system to a living equilibrium. Now, let's take for example, in this case, spirals in 2 dimensions, humans versus AI. We have all the combinations, but in here, I just chose this. The phase portrait human versus AI, looking at just human versus AI, we again see inward spirals. Without the regulator, these loops would diverge. One side wins, the other collapses. With the regulator active, the spiral shrinks towards balance. The same pattern holds for the human regulator and AI regulator projection, which I don't show here, but they are essentially the same pattern that we see in here. Okay, now for the outcome distributions, here we have a three-dimensional histogram. We have the initial AI conditions, the trial count, and the initial human conditions. And so when we ran 100 Monte Carlo simulations with random initial conditions, in about 71% of runs, humans survive at least 500 steps. So statistically, the regulatory framework favors human continuity. Analytical checks confirm that the system is globally bounded, no blow-ups, no extinction zones. Um, Now, the entropy dynamics and regulatory trigger. Next, we track the role in entropy, a measure of feedback diversity. High entropy means rich, varied feedback. Low entropy means the system is echoing itself. When entropy drops below 1.0 for too long, a regulatory flag activates. Conceptually, this prevents what I call semantic narrowing, the loss of interpretive diversity. You could imagine an entropy-aware moderator reinjecting questions or context to reopen dialogue. Now, about the energy usage divergence, AI versus humans, we're talking, imagine a situation where we have a way to measuring the meters, measuring the meters that go directly to the computers that are in charge of the artificial intelligence, and we compare it to the energy used by humans. So here we simulate the difference in energy usage between AI and humans. When delta of energy exceeds 0.5, the system flags an imbalance, too much energy concentrated in AI activity. This is not real world metering, but it mirrors what could be done with the smart grid or compute usage data. Detect over optimization before it destabilizes human systems, right? And this is, well, the explanation of well, what the plot entails. And as I say, well, which is not a real simulation, but as it is possible, it's feasible to do that with meters, how much goes to the computer, how much energy we are consuming, and then compare it. The Pareto frontier and cooperative drift. Then, well, we have run several simulations of the Pareto, and finally, the strategy selection. Pareto measures the fraction of cooperative Pareto optimal choices. Even when cooperation is available, the simulated AI drifts towards dominated or zero-sum behavior. This isn't malice, it's optimization pressure. Chamberlain predicted this. Adversarial drift can emerge from neutral efficiency. So P Pareto acts as a diagnostic for when to step in and restore cooperative balance. So this is a summary table, and all three metrics can be formalized as operators: entropy, energy, and Pareto. We have here table for each of the headers. Um, and each produces a signal when crossing its threshold, semantic, physical, or strategic. Together, they form a minimal but actionable diagnostic set for adaptive coexistence. The principle is simple: regulate the signals, not the intentions. Uh, so here we have the research code, data, and research identifiers. Well, you can right now point any cell phone and over any of the QR codes for the repository of the computer codes. Is here they are here in GitHub. Then this is the Seno.doi archive for some data. And this is a research gate preprint of all this research for which we're seeing here just a summary. And well, that's it, really. So I'm ready to take out on your questions. So let's see which questions we have. Uh-huh. This is the moment where everyone can make a question. And I've been indicated to read aloud the question so that there is no confusion what I am actually answering about. In the meantime, that anyone feels like you're going to make a question, let me make a quick recap what I say about entropy, energy, and Pareto. This is just saying that we're aware that we cannot prove completely uh, how are going to be the intentions. So we use proxies because we know that the incompleteness theorem is going to prevent to have a complete truth, and the program may never help. So with these proxies, we have a way of measuring. The first one was the species dynamics, assuming that one of them is humans, the other is the AI, and the third are the dynamics. So I say X represents humans, Y represents the AI, and Z represents the regulator, which, by the way, Professor Nira Chamberlain called it in his own simulation, which was rated a Markov chain, not exactly this type of work. He called it Obamahood, if I remember correctly. The deterministic population time series, which is the presence of a generalized regulator, leads to sustained coexistence. Um, this was the 3D spiral phase portrait. The 2D spiral, and this spiral indicating stability. This is the histogram where uh, almost regardless of the initial conditions, we have more than 2 tiers of possibility of survival according to these simulations. The entropy dynamics, which are also a way of, this is more like a trigger regulator to induce new questions, new diversity. The energy uses, we are monitoring how much energy is using the artificial intelligence. The Pareto frontier, which regardless of which way we tweak the parameters, and we always found that without intervention, then really is going always to dominance of the artificial intelligence. And in the summary, well, we have the three operators: entropy, energy, Pareto. So the rolling entropy from feedback logs, the time series energy, and the strategy selection history. So those are the three types of flags that we have. Once again, the QR codes. And now, if you download the presentation, the links are there. Those are the two choices for the code. Let me see. Can you describe the regulators more? I have one question here. Can you describe possible regulators more? Yes. Yes, I can. The first regulator about entropy, well, we see how much entropy we have at each time step. And if we go back to the slide of entropy, let me show you. What we see is that it tracks the diversity of AI feedback types within a moving window of time. So reflecting maximal diversity. So in which way we're talking about diversity? Well, diversity in, for example, responses. I'm not really doing an actual simulation of diversity, but it is possible to track if the kind of semantics is looping about a certain subject or subjects, whereas we could consider diversity when it is always trying to change the type of answers. So this was actually a simplification. So the regulatory logic applies a binary signal, S equal 1, and if H feedback smaller than H, the minimal entropy, otherwise is 0. An intervention is triggered when the cumulative sum over a window exceeds tau, flagging a persistent entropy deficit. And by entropy, we can perfectly put it in terms of the Shannon entropy or any other kind of or generalized range entropy. There are ways of measuring the types of responses, semantics, of, for example, richness of vocabulary or richness of responses. Now, the sustained plateaus above H mean denote healthy diversity, and these plateaus are well, they are not exactly plateaus like completely flat. There is one slight mountain about close to two near the towards the left, but then but it's still a sign of diversity. And prolonged drops mark semantic narrowing and activate the corrective feedback. So in here, so we get the correction of the feedback. Now, about the other regulator, the Pareto. Okay, well, we have this regulator, the energy uses. Let's suppose that we can measure the energy that goes into the computers that fit or where the artificial intelligence is set up. And we also have a way of distinguishing it from the energy used by humans, houses and the refrigerators or whatever that we use inside a house. And if we make that difference, then there is a way of see if there is a trending up of the artificial intelligence. I mean, we do know that if artificial intelligence is being used by humans, then energy is being used, and every time that something else is added, then it's going to compute to increase the amount of energy. But in here, we're assuming that AI is consuming beyond the amount of queries made by humans, meaning that is probably hoarding the energy for itself. That is optimizing just for its own sake. Um, and this is in a way related to the Pareto frontier. This is the other regulator. Uh, uh, so in here, this is also a simplification, but we assume some kind of adversarial drift. Again, most of this, if you want a more detailed way on how exactly it's coded, then everything is in GitHub. But the point in here is that we try to see if it is below a certain threshold, and then we kick in the regulator. In this case, we didn't try too much to trigger a regulator. We just tried to see if there was a stable Pareto, which it isn't. There is always an adversarial trend. Um, I know I didn't say much about Pareto because probably the code would be much more explicit, but about the energy, the entropy, and even the dynamics of the first one, the the 3D dynamics, regulated three species dynamics. Well, in here, this is self-regulated in the sense that if we establish these parameters, and we can always tweak it depending on how much we know about the system, uh, then this is a set of uh, ordinary differential equations, non-linear because they depend on each other, and thus they are dependent. So the regulator is actually this one, the z coordinate. So whenever the z the regulator detects something from y, which is here, um, then it actually then it regulates with a certain parameter beta, which we can always adjust to our needs. Now let's go to another question. Can you discuss an example scenario to apply the model? Well, I can see, for example, the fact that the AIs, any AI hallucinate up to certain percentage, and then in a few research papers of mathematics, then it has been shown by the way they make the queries that the artificial intelligence get it right in about the 2/3 of the time. That is almost the same as the chances that we have to survive, so 70%. So the way I see it is not that the artificial intelligence wants or needs to overcome humans in any way. I mean, but it is almost a given that that AIs by by the way they behave, because they are probabilistic engines, and in that sense, then it is possible that they could build up some errors. So if we introduce a regulator or these different regulators, then we could track if any AI is drifting away from the desired behavior, not just the way we see the answers, but the way the engine behaves. Now, at the moment, most AIs, they don't come alive if you don't make any query, if you don't make any questions. They are simply just staying. They don't wait anywhere. Actually, the computer is just there, but nothing really happens. However, if when we start using AIs more and more, especially with agents, then we will start seeing something like a more a continuous way of behaving, and that's the scenario where I would say a regulator with these triggers could be possible to be used. Um, and to be more abundant about that question, can you discuss an example, a scenario to apply the model? Actually, much more detail. I have answered something, but I actually wrote a preprint, a draft, if you will, of a research paper. And in there, I have quite a few other scenarios about this. In fact, I created there some semantic clouds of an example when we compare the wording of several books and how this wording can tell you if well how close it is to some kind of behavior. So these scenarios can be seen in that research paper that you can find in ResearchGate. The link to that is in the presentation, in this presentation itself. So if you download this presentation, then you will have much more detail of those possible scenarios that uh, I started to think about. Right. Well, since I don't see any more questions written in here, uh, so I would thank you all for participating. And then it is still possible, of course, to discuss this matter through email exchange or in this platform, uh, Steven. Well, thank you very much for attending.